Okay. Hello, everyone. Welcome to this second edition of the ICTS String Web Seminar Series. Today, we are happy to have Shamik Banerjee with us, and he's going to talk about BMS Symmetry of celestial OPEs. I just want to say one thing before we start. Please make sure that your mics are unmuted when you ask questions. And if at all you get disconnected because your connection is lost or something and you're out of the meeting, then if you have locked the meeting room already, then just send me an email and I'll join you back in. Okay, I'll leave it to you, Shamik.
Oh, hi. Thanks for this meeting actually. So this is the first time I'm using Zoom. So I don't know how it will go, but let's see. Okay, so I'll be talking about this recent work which I did with Shubdeep Ghosh and Ricardo Gononzo. And basically, so I'll start with some kind of brief introduction. So in this talk, I'll be talking about the scattering amplitude of massless particles in four dimensions. In that case, the asymmetric elements are functions of this on-shell momentum P and helicities sigma of the particles. Now P, since P is null, so we can write P in this form which is equation 1. And the thing is that since P is null, we can write this in terms of these spinors, this lambda alpha and lambda alpha dot. And the thing is that this Z that is actually given by this lambda 1 by lambda 2, and the Z bar that is just the complex conjugate of Z to start with, and then this is just given by lambda bar 1 dot by lambda bar 2 dot. Okay. Now in this way, so if I write P in this way, which is written in equation 1, then the S matrix, so that can be written as a function of this P, which now depends on this omega I, Zi and Zi bar and the sigma I. And note that this since P is null and in 4 dimensions, so that can be expressed in terms of the three independent quantities, which are this omega Z and Z bar. So this S matrix A, so that becomes a function of these four numbers. Now the SL2C, which is the Lorentz group in 4 dimension, so that acts on Z as Z going to this AZ plus B by CZ plus D, and this omega that transforms into omega times mod of CZ plus D square. Now this transformation, this Z going to AZ plus B by CZ plus D, that actually simply focus from the transformation law of the spinor, this lambda alpha under the SL2C, so it transforms like that. So if ABCD, if that's an SL2C matrix, then this lambda 1 prime is A lambda 1 plus B lambda 2, and lambda 2 prime is just C lambda 1 plus D lambda 2. And since this Z is lambda 1 by lambda 2, you can take the ratio of this lambda 1 prime and lambda 2 prime, and that gives you Z prime, which is essentially this AZ plus B by CZ plus D. Okay. So now let's introduce the Mellin amplitude. So this was done by Pastarsky, Shao, and Strohinger. So this is defined. So what you do is that you do an integral transform which is given in this equation 5, and these lambdas are some real numbers. But the thing is that to start with, these lambdas are real, but finally at the end of the day, you can also analytically continue to complex values of lambda. Okay, now what is the behavior of this amplitude A tilde, which is the main amplitude under the SL2C? So that is given by the 6. So A tilde, so again this ABCD, so that's an SL2C matrix, and this, so you can see that so A tilde is just given, the transformation of A tilde is given by 6, and you have some prefactors. So those prefactors we know they actually come if you transform a correlation function of a conformal field theory. And so and this I have defined some this H and H bar. So that is given in terms of the lambda and sigma. So H plus H bar, so that's the scaling dimension, and H minus H bar, so that's the spin. So you can see that, so now this A tilde, so that transforms like the correlation function of primaries with weight H and Hi and Hi bar. Okay, now we can write, so what we can do is that to make it more clear, so what we can do is that we can define the main transform of this Fock space creation and annihilation fields, which are this A and A dagger. And so this is given by equation 8 and 9. So I have just used the same notation, this phi H bar in both cases, A and A dagger. And the thing is that under the SL2C transformation, this phi transforms as a primary field. So phi just goes to phi prime, H bar, Z bar. So that is given by this equation 10. So you have this prefactor, and then the standard thing that this phi H bar evaluated at AZ plus B by CZ plus D, and so on. Okay, now this prefactor, of course, is there in the transformation of this amplitude A tilde. And since this A tilde, so now you can see this, I can write this A tilde as the correlation function of these phis. Okay, because this A tilde, so you start with the A matrix, so you have a bunch of A and A daggers, like the A out and A dagger in, and you just replace them with these phis, and then you get this A tilde in the form of this correlation function of these phis. Okay, so now what we want to do is that we want to define a slightly different phi, which now which can be defined as a time translated primaries, which are this phi H bar, U, Z bar. So it is defined in the same way, just as in the equation 8 and 9, but now you have an extra phase factor associated with this A and A dagger, which is this e to the power minus I omega u and e to the power plus I omega u. Now you can also define an A tilde, which now which is just defined as a correlation function of these phis. But now these phis depend on U, Z, and Z bar. So this A tilde now also becomes a function of this U, Z, Z, Z bar, lambda, and this sigma, which is the spin. And then you can change this integral transform. So our integral transform was like this equation 5, but now we have this extra phase factors, so you just introduce them, and then this becomes this A tilde, which depends on U, Z, Z bar. So that is given by this integral with this phase factors. Okay, this phase factor, this omega I is actually missing from equation 414, but it is just these phase factors which are there in the definition of this phi U Z Z bar, and in terms of A and A diagram. Okay, and these epsilon are some plus minus 1 depending on whether this phi is actually incoming or outgoing. Okay, so now how does this object, this A tilde, which now, so I just use the same symbol for both, like this A tilde which depends only on Z Z bar, and the A tilde which depends on this U Z Z bar. I use the same symbol, and in most of the talk I'll just be talking about this A tilde which depends on U, Z, and Z bar. So now, how does it transform under the SL2C? So this equation 15 is the transformation law. So this just gets multiplied by some prefactors, which are the same here as in the case of the A, which A tilde, which does not depend on U. But then the point is that A tilde has now a dependence on U, so all the things are same except that U now transformed by U by mod Cz plus D square. And similarly, under global space-time translation, this thing, the way this transform is that you take the correlation function of this phi, and at U and U prime, and they're the same, where this U prime has this special form that U prime is U plus some A plus some BZ plus B bar Z bar plus C Z Z bar. So B bar, at least to start with, this is the complex conjugate of B, and so you really have, so A and C are real. So these are the four space-time translations which you have. Okay. Okay, so now, so you can see, so this is a typo, so this should be U Z Z bar. So you can see that the U Z Z bar, so that can be interpreted as the coordinates of the null infinity, with U as the recorded time and Z Z bar as the stereographic coordinates of a space like cross section of the null infinity, which is called a celestial sphere. So we can see that under the SL2C, this U Z Z bar, we should think of them as transforming as written in equation 18. So U just goes to U by mod Cz plus D square, and this transformation law actually comes from the transformation law of the omega, which just gets multiplied by mod Cz plus D square. And since you have this phase factor, this e to the power I omega U, so U just gets multiplied by U by mod Cz plus D square. Okay. So there is nothing mysterious in this, of course. And then under global space-time translation, this U, Z, and Z bar, that transforms like U plus A plus BZ plus B bar Z bar plus C Z Z bar, and Z Z bar, they don't transform under the space-time translation. So this transformation of U comes from this this thing that this is the correlation functions of these phi's, they don't change. If I make the replacement u going to u prime, which is a plus bz plus b bar z bar plus c z z bar. So these are the four global space-time translation. Now these are precisely the transformation laws of the coordinates at null infinity. Okay. Okay, so now actually what we want to do is that we want to, since we have what we see is that, for example, if you don't have u, so these a tilde or the amplitudes, they transform like the correlation function of n primaries on the sphere. Similarly, with u z z bar, you have these these things look like some kind of a three-dimensional object where this phi u z z bar, that's there on the null infinity. So we can talk about the OPE just like we talk about the OPE in quantum field theory. And in particular in conformal field theory, this is particularly useful and powerful. So we want to construct, for example, the OPE of two operators, say phi 1 u1 z1 z1 bar and phi 2 of u2 z2 z2 bar. Now the OPE just corresponds to the limit where this u1 z1 z1 bar goes to u2 z2 z2 bar, but we will see that there will be no singularities in u. So all the singularities in the OPE are there in the zz bar. Now in the asymmetric side, this is the collinear limit where p1 vector and p2 vector, so they point in the same direction. So now the thing that,
Shamik, I have a question.
Yeah. Yes.
So you are not taking then u1 goes to u2 limit, right? Or you are taking?
Yeah. So in the asymmetric side, we don't have any u actually. And we will see that this u1 going to u2, so we need the u's in this case. So I will discuss this thing. But yeah, it is just easier to take the u1 to u2 actually. But yeah, like we don't lose anything by doing this. So that's what I will just after a few slides it will clear actually.
Okay.
Yeah. But the thing is that in the asymmetric side, this and one of the reflections of that fact is that you don't get any singularities in E. So all the singularities are there in terms of the ZZ bar, that is Z12 and Z bar 1.
Okay.
So in that sense, actually, U1, U2, we need U1, U2, that I will show actually. But the thing is that, yeah, I mean, and the thing is that at the end, also we will just get rid of this U. But at least in the intermediate stage, we need that actually. Yeah, so it will be clear. I mean, just after a few slides, so I'll show that how this expansion looks like. And that from there, it will be clear that why we need the U1 to do.
Okay.
Okay. Yeah. So let me just yeah. So So now in the asymmetric side, that we know that we have a
Shamik, I had a question.
Yeah.
So like before talking about this factorization and so on, is there some kind of unitarity after you deform this amplitude by this U translations?
Well, unitary, this is of course because, well, so that is hidden somehow, because what we are doing is, like, if you look at this equation 14, which is just a tilde in terms of A. A is the standard, the AS matrix. Now it is of course there. Just any integral transform will not kill this thing. But yeah, it is not completely clear that. Well, so far I think it is not completely clear that how to take that into account. But the thing is that this is of course like this can be shown actually. So this representation. So this is called this unitary principles is representation of the ASL2C. And the thing is that, so this thing, yeah, so at least when lambdas are real, it should be fine. Yeah. But yeah, honestly speaking, it is not absolutely clear that how to take that in an effective way actually. So is that?
Yeah. Okay.
Yeah. Thanks. Yeah. So I'll just yeah. So now we know that we have the collinear factorization of the amplitude at leading order, and that itself says that the OPE actually exists at least in the leading order. Now we will basically be talking about the subleading factorization. And what we'll do is that we, instead of doing it in a very abstract way, which at least I don't know like how to do it in a very abstract way. So what we can do is that we can start with the 4 graviton scattering amplitude in GR. Okay, and then so that thing is known. So it's all 3 level scattering, and the thing is that so we know what that is. So we can compute the A tilde according to this equation, and then we can take this limit when U1 Z1 bar goes to U2 Z2 bar. And the thing is that we should see the factorization there. Okay, so the 3 level 4 graviton scattering amplitude in GR. So this is actually wrong. This is not A tilde. This is actually A. A tilde is the integral transform, which is already there. So this is the A, the standard AS matrix. Okay. Yeah. So A tilde 4. So we have this minus going to plus, and this is given by this. We know, and what we want to do is that we want to take the limit where 3 goes to 4 for the A tilde amplitude. And the point is that what we basically want to do is that we want to expand the Mellin amplitude in parts of the Z34, Z bar 34, and U34. When this mod Z34 is much less than all this thing, that is Z13, Z23. I mean, which is the standard OPE in 1, 2, 3, 4. So mod Z34 is much less than Z13, Z23, Z14, and Z24. And the other point is that from now on, so we will be working in split signature, because the thing is that since I am working with a 4-point function, so it will factorize in terms of a 3-point function, and the on-shell 3-point function in minus plus is zero. So we work in the split signature, and the only difference is that now Z and Z bar, they are just independent real numbers, and this essentially follows from this. If you write it in terms of this spinors, this P alpha dot, lambda alpha dot. So in split signature, so this lambda alpha dot is not the complex conjugate of lambda alpha, and in split signature, the group is actually SL2R into SL2R. Okay, but all the things just at least for the three amplitudes, all the things just go through. I mean, you just get the same. I mean, if you write in terms of this angle and square brackets, then all the things go through. But at the end of the day, you just interpret your Z and Z bar as independent real numbers. Okay. And now we want to take these 3 going to 4 for the A tilde amplitude.
Can I ask a question?
Yeah.
So this conformal dimensions H, these had an imaginary piece, so it's not fully real.
Yeah.
So is it possible to do this OPE expansion as like decreasingly lesser and lesser divergent terms?
Yeah, just wait. So
okay.
Just wait for 2 minutes.
Okay,
so it's there. I mean, I'll just I mean that's what I will do actually. So
okay,
yeah.
thank you.
But the thing is that I want to go through this amplitude thing, like we did it in this way, because well, I think abstractly doing this thing maybe yeah. I mean, it looks almost like a conformal field theory, but there are some things which are not exactly. For example, the translations are there, so that's why we just wanted to solve this thing, starting from an amplitude and then seeing that how things go. Yeah, so that I'll do actually after a few slides. In fact, that's what I will do. Okay, so this A tilde 4, so that is the clean transform of the A4, and that I have written in terms of this G delta 1, delta 2, delta 3, delta 4. These are the gravitons, and the thing is that this is now given by this integral expression like this. So I have this Z bar 34 by Z 34, which I have extracted, and then I have this Z12 square by Z2331, and all these factors of all these factors, and then I have an integral for the T. Now this T actually in the S metric side, this T is essentially the splitting fraction. Like you write the P, you can write if P1 and P2, I mean they are just going in the same direction, then you can define a capital P, which is P1 plus P2, and then the energy is just T, some T1, some E1 plus 1 minus TE2, that kind of thing actually. So this T has essentially that interpretation. But the thing is that in the OPE limit, you can write this 4-point function, this A tilde, in terms of this integral, and you have these prefactors. And the thing is that, so this is what it, yeah. Hello. Hello. So is there any question? So this A tilde is now given by this, and this delta is 1 plus I lambda, which is the scaling dimension. And the thing is that, so let me just simplify this thing. So this integral it is not as bad as it looks like. For example, if you set Z bar 34 equal to 0, which is because you don't have any singularity in Z bar 34. So when I say that you set Z bar 34 equal to 0, what I mean is that you set Z bar 34 equal to 0 in the expression which multiplies this Z bar 34 by Z34, and then you can just keep terms in Z34 and U34, and then this integral is just generalized hypergeometric function, and it can be expanded in this way. So if you have, so this expression is much more here. So if you set just z bar 3 4 equal to 0, then this a tilde becomes, you have this z bar 3 4 by z 3 4 times all these multiplication factors, and then you have these factors, this infinite sum. Okay, so from here you can see that this has now become, so once you expand these prefactors, this 1 minus z34 by z24 and 1 minus z34 by z14, then that this is actually an expansion in terms of z34 and u34, and this is also multiplied by this a tilde 3, which is the 3-point function. So once I take 3 going to 3 plus going to 4 plus, what I get is actually a 4 plus, and that's what this a tilde 3 is. So that is the 3-point function in terms of which it has to factorize. Okay. So this expression is quite clear, like this is just depends. So this is an expansion in z34 and u34. Okay. Okay, so now let's look at the first term, which is the leading term, which is the term which multiplies basically the z bar 34 by z34, and this has this form. Now we know that, I mean, you can compute the so just let me point out one thing, that the reason I need the u's is that if you look at this a tilde 4, you will see that if you set all the u's to so then this amplitude will simply blow up, because you have this factor which is u1 times z24 by z12 plus these factors of u whole to the square, and this is 1 by u1 z24 plus this square, and then once you set all the u's to 0, then this amplitude will simply blow up. So that's why at this stage we need this u's. But the thing is that now you can see that once in the next expression, so once I write it in terms of this 3-point function, the rest of the things, so that does not have any singularity in u34. So all the singularities have somehow been absorbed into this a tilde 3, which is the 3-point function. Okay. So, but in this infinite sum, you don't have any singularities in u34. Okay, so this was the first term, and now you know, I mean, you can compute the a tilde 3, which is the 3-point function, and that a tilde 3 is given by this this equation, and so you can write the first term in this amplitude in this form, that g delta 1, delta 2, delta 3, delta 4, as z3 goes to z4, so that becomes this beta function into z bar 34 by z34 times I del u4, which is acting on this g4. So g delta 3 plus delta 4 minus 1 4, and this is equivalent to the OPE, which is g delta 3 delta 4, g plus delta 3, g plus delta 4, which is this b times I lambda 3, I lambda 4 times z bar this, and I del u4 acting on this g plus. Okay, now the thing is that you can also write it in another way, which is that if you have, if phi is a primary of weight h bar, then I del u phi, so that's a primary of weight h plus half and h bar plus half, and so this I del u4 acting on this g plus delta 3 plus delta 4 minus 1 is essentially becomes g plus delta 3 plus delta 4. Now you can see that in this form I don't need the u's. Okay, because the thing is that if you just look at this, so what will be this, what is, so let me just go back to this expression for u z z bar, phi u z z bar. So if you look at this expression, the way I have defined this phi h h bar u z z bar, now if I differentiate with respect to I del del u, what it does is that it brings down a factor of omega, and then it simply becomes omega to power I lambda plus I lambda plus 1, I lambda plus 1, and then after doing that, I can set u equal to zero, and that essentially now becomes an operator whose scaling dimension is h plus half and h bar plus half. So at the end of the day, so if I write it in this form, then I don't really need the use, but that I can do only at the end if I want to, because otherwise at this stage I still can't basically set u4 u1 into u4 to z0 because of this blowing up thing. Okay, but whatever. So this is the first term. Okay, so and then this was first actually, so this was obtained by Strominger and co-operators. So they actually found this term, but they also did much more than that. They basically found this structure constant B from the subleading soft factorization, but I will not go into that. So I'll basically look at the subleading terms. Okay. Okay, so now let's look at the subleading terms. So I have this subleading term. So you can see, so this I have two coefficients, so two functions which multiply z34, which is like z34 times 1 over z24 plus 1 over z14, and then z34 times this factor, and then I have a z bar 34, and then you can write that multiplies del del z bar 4, and then I have something which multiplies u34 also. Okay, now let's look at each of the terms. So this is a subleading term because this multiplies z bar 34 by z34, and this is a subleading term. The first term was this b times z bar 34 by z34 into g plus. Okay, now the first term, let me define something which I call this p minus 2 acting on g plus, and let me write the first term in this way. So this is the most interesting term actually, because this is because this is not the one. Okay, so I'll come to that, but let's look at the second term. So the second term is this term, which whose OPE coefficient is given by I lambda 3 by I lambda 3 plus I lambda 4 times z34 times this expression, and that can be written as this. You can write this as I del del u4 that is there, and then you just define, so this will be p minus 1. So I have just defined I del del u4 acting on g4 as p minus 1 acting on g4, but then this factor is essentially del del of z4 acting on this p minus 1 g plus delta 3 plus delta 4 minus 1 4, and then I call it L minus 1, which is the standard thing. And then of course the z bar term is also, it works in the same way. I have a del del z bar of 4, and then I have L bar minus 1 p minus 1 acting on g plus, and the last one, the fourth term, which multiplies u34. So this is the u34, and the thing is that, so this term is essentially, you can write it as I del del u4 square. So that becomes p minus 1 square acting on g plus 4. So this is the thing. So the first term is the most interesting one. So that I define this function, which is g delta 1 g delta 2 times p minus 2 g delta 3 plus delta 4 minus 1 acting at 4 is equal to this object, which is 1 over z24 plus 1 over z14 times I del del u4 into this three-point function which we have.
Sorry, Shamik, I missed what is your definition of this p minus 2 and so on?
Yeah, so the p minus 2 is let's just I mean for the time being, I mean let's just think of it as some symbol, and whose only thing is that if p minus 2 acts on g plus, and if you compute this three-point function g delta 1, g delta 2, and p minus 2 g delta 3 plus delta 4 minus 1, then that can be written as 1 over z24 plus 1 over z14 into I del del u4 acting on the three-point function g delta 1, g delta 2, g delta 3 plus delta 4 minus 1. But now I will come to that where this p minus 2 will come from actually.
Okay.
So for the time being, let's just think of this as some symbol. But the thing is that the physical interpretation of this will come now actually. Okay. And the physical interpretation of this L minus 1 and L bar minus 1, these things are of course clear. Because this is just del del z4, this is del del z bar 4, and I have this I del del u4, and the prefactor is also the same as I del del u4, and I have this p minus 1 square.
So one more question. I should have probably asked you a little bit earlier, but when you write this 4-point function, can you write the whole thing in terms of cross ratios, like if I took Z34 by Z24 or something?
Yeah, that actually I think, yeah, I mean if you compute it exactly, then you can do actually, yes, of course you can do, and there are some constraints like for the 4-point function the cross ratio has to be real. But the thing is that what we found is that for the OPE expansion, that form is not very useful. So it is just more useful to actually write it in this form, in the way I have actually.
I see.
But you can actually, yes, you can write it in terms of z and z bar, and you have this standard factors which multiply this 4-point function. Okay.
I see. But for the expansion you're doing, you say it's not very useful.
Yeah, it is just simpler. So we tried to start with actually we tried to start from that 4-point function and expand it. But it seems that if I write it in this form instead of starting from that exact 4-point function, if I start with this form, then the OPE expansion is extremely clear. Like we already have something in increasing power sub Z34, U34, Z bar 34, things like that.
I see. Okay, thank you.
Yeah. But yes, you can do this thing actually. Yeah. So now let me come to the interpretation of this p minus 2. So this p minus 2, that actually, so that turns out to be a super translation descendant. So how do I know that? So you start. So this is of course the well-known thing. I think the first thing which Strauss-Straussinger found is that this Weinberg soft graviton theorem. So that can be thought of as the word identity for the super translation. And this has this. So if you start from the soft theorem, then you can write this. You can write the soft theorem in this form, that this PW, which is the super translation coefficient, and this PW multiplying this phi is just given by this form, this 1 over W minus ZK times I del UK acting on this, where PZ is given by del bar of S plus ZZ bar, where S plus is the positive helicity leading soft graviton. So now this from now, if you look at this word identity, you can easily see that where this structure of P minus 2 come from. So let's do the following thing. So just yeah, so if you start from this word identity, then you can, so if epsilon W, if that's an analytic function, so these things are all very standard. So this is equivalent to the symmetry transformation, that is delta of phi h bar u z z bar is epsilon z times this. So geometrically this corresponds to this super translation, where epsilon z is an analytic function. And we can also define in terms of modes, that is, I can define a delta k acting on phi h bar as I, so I can take epsilon z to be z to the power k plus 1 and define this I z to the power k plus 1 del u, and you can formally define a commutator of pk with phi, which is just given by this I z to the power k plus 1 del u acting on this. So this pk, so that's the generator of the holomorphic super translation. Now you can see that this p minus 1 is now simply I del u. So that is a time translation, and that is this thing here, which I have like this p minus 1, or this p minus 1, or this one. So you can see it is just I del u4, which is the same as this. If you set k equal to minus 1, then z to the power k plus 1 is 1, and you are just left with this I del u5, which is the time translation on phi. Okay, now we need to find out this p minus 2. Now p minus 2, you can look at this. You can see this. If I set k equal to minus 2, I get a 1 over z, and that has a singularity at z equal to 0. So how do I get this p minus 2 acting on phi? So how do I get this thing? So this is also the standard trick that we use, that we have this. So we define the OPE of this PW and some primary phi, which has this form. So p minus 1 phi. So we know, so the residue of the pole is just p minus 1 phi, which is just the translation in time, which you should have. And but then there are all these non-singular terms in the OPE, and of course, you know, the standard thing is that the non-singular terms in the OPE, they basically define the descendants, which are created by singular transformations. And in this case, so p minus 2, it's a singular super translation, because here epsilon z is just 1 by z, so u goes to u plus 1 by z. So that's a singular super translation. And now how do I find this p minus 2 acting on phi, the correlation function of that, because that's what I need to find. I need to find this thing, the 3-point function of g delta 1, g delta 2, and p minus 2 acting on this g plus. Okay, So that of course also is standard. I look at the word identity. I take this phi u z z bar, and then I have a bunch of fields, some bunch of n fields. I write down the word identity, and then I take this w to z. So I do the OPE of PW and phi u z bar. So on the left hand side, I substitute this OPE, which is there in equation 40, and on the right hand side, I do an expansion in powers of W minus Z. And so if I do that, and then if I compare the coefficient of the equal powers of W minus Z on both sides, then what I get is this equation 42, and this basically tells me that P minus K acting on phi. So this is a descendant field, and its correlation function is actually given by this sum. So now you can see that if you set k equal to 2, so you can see this structure, which is 1 over like Z14 and Z24. So that's what we have actually. So in our case, n is equal to 2 and k is 2. So you can substitute this, and what we will get back is essentially this expression which you have here. Okay, except that now you have to use the explicit form of the 3-point function to write this thing, that this 1 over Z24 plus 1 over Z14 into I del del U4 is, when it is acting on the 3-point function, it is the same as 1 over Z24 times I del del U2 plus 1 over Z14 times I del del U1. Okay, so that's a for that you have to use the explicit form of the 3-point function, which we know. So this is the, so we got this P minus 2 phi. So now let me write the OP in this form. So I have G delta plus G delta 3, G delta 3 plus G delta 4 plus. So that is, so a part of the OP, the first subleading terms. So those are given by this B times I have P minus 1, P minus 2, L minus 1, P minus 1, and L bar minus 1, P minus 1. And we can see that this P minus 2, that gives a holomorphic super translation with pole. Okay. So now you can look at, so now actually you can look at that this OP expansion. So there, so if you look, okay, so let me now look at the recursion relation for the OP coefficients. But let me just show you one thing, because there was a question which says that if this is in increasing powers of the scaling dimension. So from here you can see that this is in the increasing power of the scaling dimension, because P minus 1, so that has scaling dimension half. So it actually follows from this algebra. So in particular, you can look at the scaling dimension of the P's. So that is given by L. The scaling dimension of PA is A plus the H for the PA is A plus half times the A plus half, and the H bar for this is half. So P minus A has scaling dimension A minus half and half. Okay, so P minus 1 has scaling dimension half. So now you can see that where you get this thing. So P minus 1 has scaling dimension half. P minus 2 has scaling dimension 3 by 2 half. So that is what the Z34 times P minus 2 is. So I just write it. So Z L minus 1 P minus 1, that has scaling dimension half. Similarly, Z P minus 2, that also has scaling dimension half. So you get like just it's the same thing that you get in a conformal field theory, that this is actually scaling. I mean, this is in increasing powers of the. I mean, this is in increasing powers of the z or z bar or u, and the operators which you have, which you get, they also have increasing scale dimension. Okay. So that's what we do now. Okay, so we have to. Okay, so I think I just need two more minutes. So this is the BMS algebra. Just the, so I don't write the ALN bars here because that's I'll not use that in this talk. I mean, I just look at the coefficient of the Z34. Okay, and I use this algebra. So I start with this. So this is the leading order OPE. So now I start doing this in an abstract way. So I start with an expression like this, and then I ask that what are the operators that can appear in the z cube order at z, and then at z, if I just look at all the descendants I can see that I have only two, which is L-1, P-1, and P-2. And then I start with this, that I write these terms with some unknown coefficients, which are C1 and C2. And then our job is to find out C1 and C2. And the thing is that in this case, it turns out that you can just get C1 and C2 just by applying L1 and P0. Okay, so both have negative H bar, negative H. Now, of course, now the things are extremely standard. So you have this L1 commutator phi, P0 acting on phi, and then this L1, we know that L1 commutator phi is 0 is equal. Similarly, P0 is the same. And then we do the standard procedure, and what we get is C1 and C2. Okay, now this C1, C2, so that of course exactly matches with what we have here. So you can see this is I lambda 4 minus I lambda 3. So just replace this lambda 4 by lambda 2 and lambda 3 by lambda 1, and then you get the C1, C2. Okay, which you have. So you can actually get it in this way, and you can also get the coefficients of z bar and also U34 in this way actually. So the U34 coefficient you can also get. I mean, U34 means P minus 1 square, so that you can also get in this way. Okay, so this is how the OPE actually works. Yeah, so this is actually, I think I don't have any more time. So yeah, so I think I'll stop here because yeah, so the rest of the things, yeah. So thanks. I think I'll just stop here.
Since we started a couple of minutes late, maybe you can take.
Oh, okay. So that is fine. So the thing is that well, the rest of the coefficients can be obtained in the same way. But the interesting question is that what happens at higher order. So now it seems that we have a reasonable answer to that, and we have checked it up to z cube or z squared z bar thing, and it again factorizes